So this unit deals with the three-phase circuit and its applications and its connection types. So before we move to the three-phase connection, we should understand what is the need of this three-phase supply system and what are the applications of single-phase systems and where this single-phase system is not fulfilling the demands with respect to generation, transmission, distribution, and different applications. Okay, so in general, the single phase applications which we can easily see in our home, that we have different kinds of motors which are used for mixers, coolers, fans, AC, refrigerators, etc. But the rating of these applications are less. Since the rating is less, so the working efficiency is also less. Okay. So when we talk of the polyphase system, it means when we are talking of more than one phase. If we are required to supply the power to electric furnaces, two-phase system is generally employed. Similarly, six-phase system is usually applied, employed in connection with the converting machinery and apparatus. Okay, which means that the three-phase supply is the base supply from which the two-phase supply and the single three-six-phase supply can be obtained. Okay, so what do we understand by the polyphase system? It is just as we have discussed in the single phase system also. uh, you can say that there is a conductor which is moving, say, in anti-clockwise direction in the magnetic system. So when there was a single phase system, there was only one conductor which was moving. Here we are talking about the three phase generation. Okay, but if we are talking of the two phase generation, then these conductors will be two, and by default we take the anti-clockwise direction. Similarly, for three phase system, there are three conductors which are pivoted at a particular point. Okay, so more are the conductors which are moving in the magnetic system, more they are cutting the flux which is passing from north pole to south pole. Okay, so more is the flux cutting, more is the EMF generated. Okay, so this is the basic concept of the three phase generation system. So three phase is generally denoted by R phase, Y phase, B phase. So next is the symmetrical supply system. So a symmetrical supply system is when several voltages of same frequency have equal magnitude and are displaced from each other by equal time angle. Okay, so frequency should be same, magnitude should be same, and equal time angle means that they will pass the reference axis after the equal interval of time. Okay, and since this time and angle are convertible to each other, so we can say that they will cross the reference axis after a fixed angle. Okay, so in the supply system, generation is clear to you. Now we move on to transmission system. So the transmission system may be of three phase, three wire system. Wires will be of three phases, and in case of three phase, four wire system, the fourth wire is neutral wire. Okay, so this here we are talking of the single circuit line, but if we are talking of the double circuit line, then the phase wires are doubled. Okay, the three phase three wire system will be converted into three phase six wire system. Okay, and similarly, this is also visible if you closely monitor the transmission lines. Okay, and this three phase four wire system is also applicable in distribution system, and in our energy meter also it is specified whether we are using the single phase two wire system or three phase four wire system. It is also mentioned there as well. Okay, supply. So when we talk of the unbalanced supply, a three phase supply will be unbalanced when either of the three phase voltages are unequal in magnitude, or the phase angle between them is not equal to 120 degrees. Okay, since we have just discussed that the balance system or the symmetrical system should have the same angle. Okay, so if we are talking of the same angle, and in the one circle we know that it is 360 degrees, so if we divide this 360 system by three parts, then it becomes the three, you can say that these are three phases. So they are separated by 120 degrees each, as shown here. Okay, so this is the phasor representation of three phase system. So if either this angle is less or the magnitude of the voltage, okay, so it is VB, VR and VY. So these are the RMS voltages. So if either this is not equal or angle is not equal, then we can say that it is unbalanced supply. Okay, so generally I have just mentioned we have taken the, we take anti-clockwise direction. So with reference to the reference axis, say x-axis is generally taken as the reference axis. So R phase will cross the x-axis, then it will be turn of the y phase to cross the reference axis or x-axis, then it will be the turn of B phase. Okay, so if this is happening, then we can say that the phase sequence is RYB. Okay, but if at all this Y phase and B phase are in this fashion, then we can say that the phase sequence is RBY. What is this balanced load circuit? Till now we were talking of the balanced supply or three-phase balance supply. Similarly, the three-phase balance supply is connected to three-phase balanced load. As in the case of the single phase, we have observed that the single phase supply system is connected to the single phase load. Similarly, supply is connected in into the three phase load. Okay, so these three phase load can be resistive, inductive, capacitive, or a mixture of those. So we can say that we can calculate the impedance of the load as and when needed. Okay, so a load circuit is said to be balanced when the loads connected in the various phases are same in magnitude and as well as in phase. This is say our supply system, and it is having three phase system, and say this is our R phase, Y phase and B phase. And if it is connected to a balanced load, three phase load, it means that R phase is connected to R phase, Y phase is connected to Y phase, and B phase is connected to B phase. This is our supply system. This is our load system. Okay. So similar to the supply system, if these impedances are same, then we say that it is balanced load circuit. Okay. And in case one of these three phases are out or a faulty system, say this is the system is faulty, then the system is called single phasing. Okay, so either we can connect the three phase load to the three phase supply system, or we can say that within a house as well. Suppose there is a 2 BHK house, then the two phases are connected to the two rooms and one phase is connected to the say hall system. Okay, so if at all one of the phase is not available, still there will be a supply at two other phases, so it is advantage. So what are the advantages of the polyphase system over single phase system? It is listed here. So in the single phase circuit, the power delivered is pulsating. Okay, why it is pulsating? As we have calculated the instantaneous power for different loads in single phase system, we have observed that the instantaneous power is equal to the product of the instantaneous voltages and instantaneous current. And since the instantaneous voltage and current go for the zero crossing, so at that moment the power delivered will also be zero. Okay, so what we can say that even when the current and voltages are in phase, the power is zero in each, zero twice in each cycle, and the when the current leads or lags, the behind the voltage the power is negative twice and zero four times during each cycle. Okay, suppose that we are talking of the uh, resistive load. So if we are talking of the resistive load, we have observed that this is the, say, voltage waveform, say this is current waveform. Okay, since they are in phase, so from 0 to 2 pi, we are not taking this 2 pi as 0, because it will be the part of the next cycle. Okay, if we are taking this, so simply it is they go 0 to 2 pi. Okay, so if we are taking this as square bracket, it means that we are including the 0, then this 2 pi will be in round bracket, or this is not included. But reverse is also true. If you want to take this as round bracket, then you can take this as square bracket. In this case, this 0 part will be part of the previous cycle. Okay, so you can do either way, but the fact remains same, that the zero crossing of the instantaneous power will be twice for each cycle in case of resistive load. Okay, but if the load is not resistive, it means that the voltage or current, uh, they may be leading or lagging with each other. Then what happens? The power is negative twice and 0 4 times. Okay, because say V is equal to Vm sine omega t, and this is current is omega t minus, say, phi. Okay, okay, so time is 0 at 0 and pi, so it will become 0. And when this omega t is phi, it will become 0, because say it is the inductive load, so this is, say, voltage, so current is lagging, so it will, say, begin its journey after, say, phi angle, and similarly it will end up, so here it is 0. Okay, so when the omega t is phi, it is 0, and when the omega t is pi plus phi, it is again 0. So the voltage and current are 0 at 4 points. Okay, so power will also become 0 at these 4 points, and it is also negative twice when the load is small, as in the case of our single phase load, our at home, you can say, which is loads using small motors and the lighting system, it is not much objectionable. But in case of large motors, excessive vibrations are there. Okay, so it will result in the noise. Okay, but in case of polyphase system, the total power delivered is constant. Okay, so it is advantageous. Okay, the rating of the given machine increases with the increase in number of phases. Okay, so which means that this, if we are using three phase system, three phase load, it can have the higher rating system. Okay, And single phase induction motor, make a note of the short form which is used here, IM. It is induction motor. Okay. So the single phase induction motor have no starting torque. Okay. So the auxiliary means are required for starting. But in case of three-phase motor, except in the synchronous motor, there is no need of the providing these auxiliary means to start the motor. Okay. So this is a good point. So what is the auxiliary means? The auxiliary means is nothing but we can provide the capacitor. Okay. So a capacitor is provided. So it will provide the starting torque. So the power factor of the single phase induction motor is less than the polyphase motor of same rating. Okay. Power factor is also less, efficiency is also less, and the three-phase system requires less amount of conductor for transmission. Okay, and also the polyphase system is more reliable and capable than the single phase system. Parallel operation of polyphase alternators is simple than the single phase alternators. Okay, so the three phase alternators can be joined parallelly, okay, for more reliable operation and backup provision. Let's first begin with the generation of single phase EMF. So here this generating machine is there or alternator is there, north pole south pole is there, and the magnetic lines of forces or the flux is trying to reach from north pole to south pole, but in the given figure it is blocked by the conductor whose sides are A1 and A2. Okay, so this derivation we have also done in previous unit as well. Okay, so when it is blocking all the flux which is linked to what is happening, d phi by dt is 0 or EMF is 0. Okay, now the anti-clockwise direction is shown in this diagram as well, and also in case of the phasor diagram. Okay, here also it is, this is the phasor diagram, anti-clockwise direction is shown, in diagram is also shown, and in waveform also we can see that the angle with which the conductor is changing its position is in synchronism with its position. Okay, so and also we have correlated this thing earlier also, that if any rotating phasor, this is the phasor is nothing but the imaginary rotating line. Okay, so if it is completing the whole circle, so it is completing the 360 degrees and it can be related to our waveform. Okay, so it gives the instantaneous EMF as EM sin omega t. Okay, now we move on to the generation of two-phase EMF. So what is happening is in two-phase EMF, nothing more but that the single conductor is now replaced by two conductors, and the terminals of the second conductor is named as B1, B2. Okay, so they are shown here, and phase difference between them is 90 degrees. Okay, so zero crossing will be after 90 degrees. Say if the zero crossing is in the x-axis A2, then the B2 will travel after 90 degrees. Similarly, if we see that A1 is here, then the B1 will travel after 90 degrees. Okay, which means that at every point the EMF will be traveling after 90 degrees. Okay, so if the magnitudes of this EMF is same, then there is a no problem. But if the magnitude are different or the maximum is different, it becomes like this. Okay, so second phasor or second conductor is moving after 90 degrees, so it will end up also after 90 degrees. Okay, so we can show this in the waveform as well as in the phasor diagram. So phasor diagram will show the E A1 A2 as the RMS value of the EMF of first conductor, and this is the second conductor EMF RMS value. Okay, so we can also say that E instantaneous values are Em sin omega t, and the second is Em sin omega t minus pi by 2 if the Em is or the maximum value is same. Okay, so if we denote it as phasor, then E A1 A2 is equal to EP any phasor, and second is lagging by 90 degrees. Okay, and using vector algebra we also know that we can also denote like EP e to the power minus j 90, and vectorially we can represent it as minus JEP. Okay, this is using de Moivre's theorem which you have studied in 12th class, that e to the power I theta is equal to mod of E bracket start sin theta plus cos theta. Okay, similarly now we move on to the generation of these three phase EMF. What is happening here? There are three conductors which are separated each other by 120 degrees as shown in the diagram. So zero crossing will be after 120 degrees each. This is the EMF waveform instantaneous. So one will begin at 0 degrees, other will begin after 120 degrees, the third will begin after 240 degrees. So here is the zero crossing, or it will begin from here. Okay, then we can complete the sine wave. Okay, similarly here phasor diagram, these are three phasors shown and they are moving in the anti-clockwise direction. So we can say if the one is Em sin omega t, then the other is Em sin omega t minus 2 pi pi 3 or 120 degrees, and other is minus 240 degrees or minus 240 we can say, or plus 2 120 is all the same. Okay, we are talking about this phasor, so we can say that either it is lagging by 120 degrees or we can say that it is leading by 120 degrees. It is all the same. Similarly we can represent these as in vector form, EP minus 120 degrees minus 240 degrees or 120 degrees, and using de Moivre's theorem E is equal to I theta is equal to mod plus sin theta plus cos theta, same. This angle 120 degree is substituted here. Okay, you can calculate sine 120 degree and cos 120 degree and justify these yourself. Okay, so in the balanced system the resultant is 0 because if say this is 1, say this magnitude is 1, then this is also 1, this is also 1, but now the angle between them is 120 degrees, so angle between them and the negative of the x-axis will be 60 degrees. So if we take the cos component, so it becomes minus 1 by 2 due to this phasor and minus 1 by 2 due to this phasor. So one this 1 and this minus 1 cancel out each other to give the resultant EMF as 0. Okay, so the algebraic sum of the three EMFs at any instant is 0. Phase sequence I have just explained you.